Okay, what's today's topic? Correlation. Correlation, what's that? Correlation is, well, if you have a correlation, it basically means that one variable, whatever it is, temperature, whatever, one variable seems to predict another. One variable seems to predict another. When you get a lot of these, you get a lot of those. Or it could be, when you get a lot of these, you don't get very many of those. One kind of cancels the other or something. In fact, let's just skip down to the bottom here, right down there. The predictor variable, let's just say that's x. Usually x. On the x-axis, we put our predictor variable, and then the other one, the y, is called our response variable. So predictor variable, when I set x equal to this, I get a response. Y is equal to this. That's kind of all that's saying. So let's see now here. Let me maybe draw something like this. So you have your x-axis here, you have your y-axis here, and you have maybe a bunch of points, a bunch of data points, and let's say they just happen to line up beautifully like that, right? So if they line up beautifully, that means if you know the value of your predictor variable x, you can use it. To basically, what do you want to say? Discover the value of the response variable, y. Now I have a special spot at the bottom of the page to say that because we want to make this part clear. We are not saying that one causes the other. Only that there is a relationship. They occur together. Only that they occur together. No, I like the first thing I said. Only that there is a relationship of some sort. Or in this case, a linear relationship. Remember the idea, correlation does not imply causation. So if you have a correlation, even if it's a very strong one, that doesn't mean that whatever x is causing y to take on certain variables. You set x here and it causes y. Don't say cause. Don't say cause. We're not saying one causes, only that one sort of predicts. It predicts the other. They happen together. They just, for some reason, something's going on, they happen together. There's a relationship there. Okay, so let's say you have two variables, an x and a y, and you have some data points and so on, and you're curious. You're saying, I wonder if there's a linear correlation here. Well, the first thing you should always do, and this is really good advice, first thing always, look at the scatter plot. People can give you all kinds of summary statistics to try to talk you into it, but there's nothing like a good scatter plot to show you exactly what's going on. So let's see, what's going on here in this first graph here. Well, those sure look lined up. Looks great. That looks wonderful. They look correlated. Looks like I could tell you the value of x and you could tell me the value of y. That goes with it. Now this isn't bad, right? You can picture a line kind of going through the middle of the points like this. That's still pretty strong. So you can state your variable, your value of x, maybe it's this, and the line will give you a value of y, and you know that it's going to be in the ballpark, right? It's going to be really pretty close, actually, because it's such a strong, well, correlation. It's still pretty strong right there. Now over here, yeah, you could put a line through that, and it would kind of work okay, and I'll just say pretty much. There's pretty much, it looks like a correlation here, right? Doesn't it? Now wait a minute, when you get over to here, and actually, you know, I kind of wanted to draw like more points. So just kind of draw a whole bunch of, and they don't have to be regularly spaced. They can just be some kind of a random cloud or something of data points, right? I dare you to put a straight line that fits all of that data very well. So there is, I'm just going to put nope. There is no correlation between the x and the y there. Okay, next row. So here's another one that looks really great. Notice I don't care whether it goes up or down, just that they're on a straight line. Looks great. We would say these two variables have a strong linear correlation. This is still pretty strong, right? What did I do? Just flip one over? Anyway, still pretty strong. Again, it's going down instead of up, but we don't care. It's just, are they on a line? That's the only question. And here, pretty much, right? You know, pretty much. So there can be strengths associated with, you know, how strong is the linear correlation. If they all line up, oh boy, that's a strong correlation. If they don't, it's like, well, it might still be a correlation. If they don't line up, like over here, then no way. And then look at this. This one over here. You know what that is? That's a parabola, or at least that's what I had in mind. And so, yeah, there's a pattern, all right. There's a nice pattern. But it's not a line. It's not a line at all. I mean, I defy you to put the best line through. What would you do? Go something like this, or maybe something like this? There's no one line of best fit here. So there's no linear correlation. So you'd say, what do you want to say? Put it over here. No linear correlation. You might say, look, there is some kind of correlation here. It's just, it's not a straight line. It's a parabola. It's a something else. But we're more concerned with linear fits in today's lesson. So, okay, so that's the idea. If you look at the scatter plot, which just means graph the points, if you look at a scatter plot, you can pretty much make up your own mind. Yeah, I think there's a really good correlation. Yeah, there's a correlation. Yeah, that's not a line. That's a cloud. That's a parabola, whatever. So associated with these plots is some terminology we want to get used to. So what does it mean, positive versus negative correlation here? I want to make a point because people mix this up a lot. All this means is whether the line goes up or down. That's all it means. It doesn't have anything to do with, is this a really good one, positive, or is this a really bad one, negative? It doesn't go like that. It's just, is it up or down? Is whether the line goes up or down. I love it when they sharpen these Apple pencil things. Anyway, when the line goes up, positive slope, in other words, a positive slope means a positive correlation. That's what it means. These variables are positive, have a positive correlation. Or if the line goes down, if it goes down, meaning it has a negative slope, then it has what we call a negative correlation. So up here, maybe I'll change colors now. This would be I would write a perfect positive correlation, whereas this would be a perfect negative correlation. They're all perfectly lined up. This one goes up, this one goes down, that one's positive, that one's negative. This is a strong positive correlation. This would be a strong negative correlation. And this would be, pretty much, this is also positive, this is also negative. I wouldn't say it was strong. But, it's not bad, but, hey, it's not bad. Okay, what else we got? Strong versus weak. Oh, I guess I was already kind of using that, wasn't I? So strong just means really lined up nicely. That would be a strong correlation. So I said this one was perfect. If they happen to be perfectly lined up, I guess you could call it, it's so strong, it's perfect, right? But if they're really closely lined up, you could still call it a strong correlation. A weak correlation would be more like this. That's a little weaker, kind of a weaker correlation. So really lined up nicely versus a weak correlation would be not so much. There's a little more scatter to it. Bit more scatter to it. That sounds good. Okay, so we're just learning to use the words correctly. Positive versus negative just means, does it slope up or does it slope down? I guess a positive correlation, you could look at it this way. When I make x a bigger number, y is also a bigger number. That would be a positive correlation. Here it's like when I make x into a bigger number, actually my y comes down. So they're going in opposite directions. You make x big, it makes y small. So that's what a negative correlation means. But again, it means a negative slope. That's all it means. Zero linear correlation. Well, we had two of those, right? So we had up here, that's not a linear correlation at all. It's not a correlation of any kind. This was, you might argue there's a correlation there, but it's not a line. So really there's two cases to this. Zero linear correlation, you could say either it's a random cloud, random scatter, or maybe that's a nice pattern. Just not a linear, just not a line. And I'll put here parabola or something, which is what we had above. Okay, and then we already talked about predictor versus response variable. Cool. So that's kind of the lingo that goes with correlation. And I want to emphasize this. The best way to find out if you have a linear correlation going on is to graph the darn thing. Just make a graph, because that will give you an intuitive feel for, are these things, does one predict the other? Is there a strong linear correlation? Could I fit a nice line to these data points or not? Okay. What's going on here? Oh yeah. So now that you kind of have this idea of, well, I could look at it and tell, it'd be nice to have something a little more objective, right? An objective measure, a number you could crunch that would tell you whether a correlation counts as weak or strong. Well, there is such a number, and it's this number. It's called the Pearson product moment correlation coefficient, which nobody's ever heard of before. It's a little r, which everybody's heard of before. Anyone who's done this kind of, finding lines of best fit, they've heard of the r. If you haven't, well, we'll deal with it now. So this little r is a number. It has a name, Pearson product moment correlation coefficient. But what that number does is it tells you how good the fit is. So let's see here. How do you get the r? Well, there's a hard way to get the r. You could convert your x data to z-scores and your y data to z-scores and then do this weird formula. Let's not. We're not going to do that. But I put this diagram here just to kind of show you, why is it called a product moment? Moment is kind of like torque. What it does is it kind of says it takes this data point, right? And then it takes, this would be the zx, this would be the zy, and it multiplies them. It's almost like a torque. If you ever torqued on a wrench, the further out that you put your hand on the wrench and the harder you push, the more torque you get. So this gets a positive contribution to torque. This one gives you a positive contribution to torque, right? And then this one gives you a negative contribution to torque. And anyway, there's some magic way that they add up all these torques and they come up with an R. The R, by the way, this is important, the R is always going to be, I shouldn't put a 0 there. The R is always going to be between -1 and +1. That's worth putting in a box, actually. +1 would be a perfect positive linear correlation. And a -1 would also be perfect, but it's a perfect negative linear correlation. So being out at a -1 or a 1 is a perfect correlation. R equals 0 means no linear correlation. So actually, let's come back to page 1 because I want to kind of put numbers on this graphs over here. So this would be like R equals +1 because it's a perfect positive linear correlation. This would be like R equals -1 because it's like a perfect negative linear correlation. This would be pretty good. So it might be R equals, I don't know what it is. Let's say it's really high, it's 0.95, and then this might be like -0.95 or something like this. This one might not be quite as good. Maybe it's a 0.7. This one might be a -0.7. This one is going to be a 0. This one is going to be a 0. So this is how the R's work. Again, a +1 or a -1. They both count as perfect fits. All the positive and negative tells you is which way it goes, up or down. That's all that part tells you. A 0 is when you have no linear correlation. So anyway, okay, so the R is going to come out between -1 and 1. And again, you could do this funky thing if you want. You got some time on your hands or whatever. But we're going to do it the easy way, which is to ask Excel, and that's what I'm doing over here. Let me change colors. So this is a view of an Excel spreadsheet, and we kind of had to run off to Excel in the last homework just to calculate. What did we calculate? Oh yeah, we calculated an area left for a binomial distribution. Yeah, whatever. We went to a single cell in Excel and typed equals and put this formula in, right? Well, this time we're going to have to type a little bit more. So let's say you've got some data. So notice I got some X and Y data. Now the X here and the Y here, you don't have to enter the X and the Y if you don't want to. I just like to put these labels in my Excel spreadsheet so it's easier to, if I open it up later, I'll remember what I was doing. But I've got the point x is 3, y 48. I've got the point x is 3, y is 45. I've got the point x is 5, y is 34, x is 12, y is 8, x is 17, y is -4. Okay, cool. So what I did is using 2 columns, I put my XY table in for some data points. Then again, you don't have to enter this part. I just did. I said R equals, and then this. This is the thing we have to, this is the hard part. You have to enter this in here. Now, when you type this in, it's going to spit out this number, and that is your little r. Notice we got an r of negative 0.9899. That's a pretty good correlation, I think. So how do you use this thing? So you come to this cell, you type the equals. You have to type the equals because that's what tells Excel to do a calculation for you. You have to type this word in, Pearson, and I think it has to be capitals, though I'm not sure. And you have to open up a parentheses. And then when it says X range, what you do is you take your mouse to cell, this is cell A2, right? A2. This is cell A2. You click and hold. And when you hold, I don't know what I'm doing now, but when you hold, you drag the mouse down to here, and then you release. And so that little range of numbers will be stuck right there. Then you have to type the comma, or maybe there's a comma there already, I forget. But anyway, you have to type a comma there. And then the Y range. So you just come over here, press the mouse on the 48, hold, and then drag down and let go. Is this really magnifying? I don't know. Anyway, and then you'll have your Y range. And then you might be able to just hit equals, or you might have to hit the closing parentheses. I don't know. So when you do that, boom, you should get that R value right there. Cool. That's how you calculate the R. So it's just run to Excel and put some numbers in and ask. That's all it is. So we might as well use the Excel. We've all got Excel, right? Okay. Now, once you've got that value of R, now I was giving you an idea back on the first page, right, that something like +1 means perfect. Something like 0.95 usually going to mean pretty good. 0.7 is going to mean, well, it depends though. It depends though. It depends on what? It depends on how many data points have you got, and it depends on what significance level do you want to talk about. So this, I'm going to go to green now. These numbers here are alpha, or the significance level. Remember hypothesis tests? We would choose a significance level, like we're going to reject the null hypothesis if alpha is, we're going to use alpha equals 0.05. So if the p-value is less than 0.05, if the p-value is less than 0.02, and so on. And so these were the alphas we would use. And then this is kind of getting at the p-value, although not directly. These are not p-values. These are R values. These are critical R values. In other words, you need R to, doesn't look like the word need, does it? Need R to be at least this big to call it a significant, statistically significant, I guess, linear correlation. So what do we have? We had, well, you have to count the data points. 1, 2, 3, 4, 5. We had 5 data points. So I'm coming across on 5. I've got a negative point. The negative doesn't matter in the table. 0.9899. All of these are less than that. In other words, I need to have at least, let's say I want 0.01 significance level. I need to have at least a 0.959. Have I got at least a 0.959? I got a 0.989, for goodness sakes. So yes, this is a statistically significant linear correlation. Yes, it is. Yes, it is. So that's our process. You go to Excel, you type your data in, then you come to a different cell and you type the Pearson formula in and get your R, and then you come to this table and you cross-reference with the number of data points, with the significance level, and you look this up. This is a critical value, which means your R has to be higher than that for it to count as a statistically significant linear correlation. Okay, so let's get rid of some of this stuff. Try to clear up our graph just a little bit here. I got 2 more examples down here. Whoa, Nelly. So let's go back to blue. Biff plots height versus shoe size. Okay. He's got 4 data points. Okay, what's that tell me? That tells me I'm up here in the table. He gets R equals 0.962. Nice. We'll have to compare against the table. Does this count as a statistically significant linear correlation at the 0.05 level? So he's talking 0.05 level, 4 data points. So the table says needs R equals 0.950. What he has is a 0.962. Yes, it counts as a statistically significant linear correlation at the 0.05 level. So once you've got your R, it's really just a matter of looking in here to see if the R was big enough. And if it was, you can say, hey, we got a linear correlation going on here, and it's statistically significant at the 0.05 level. Less than 5% chance we're wrong, which is basically a loose way of interpreting alpha. I'm accepting a 5% chance of being wrong. Well, what could he do? 0.962. He could do... Well, I guess he couldn't do a 2% chance of being wrong, would he? He didn't make it that hard. Didn't make it that high. Oh, well, I was hoping he could have used a better significance level, but he can't. Bjorn plots 30 pairs of values. So Bjorn is down here, looking for a linear correlation between the screen time spent on TV, internet, phone, versus GPA. He gets R equals, and he's got a negative, but again, the negative just means the slope is negative. It doesn't, you don't use negatives in the table. But he got a 0.483. So at the 0.01 level, so 0.01 level is this last column, he would need a 0.463. He has a 0.483. He made it. He's got higher than the value in the table. So another yes. And again, the negative only means that it's going like this, that it's got a negative slope. I don't know what the slope is. This is not the slope, by the way. This is just telling you it's well enough correlated. So it might do something like, I don't know what it does. It's not perfect. It's not -1, but there's a correlation there. It counts as statistically significant at the 1% level, 0.01 level. Wow. Okay, that's how you kind of do these things. So before I let you loose on the homework, some notes of caution here. Caution in purple, sure. Notes of caution. Like I was saying on page 1, it's always best to do a scatter plot. You can just type numbers into your Excel spreadsheet, ask it to give you an R and look it up and all that stuff, but you might miss something. If you just trust the calculator, you might miss something. Always do a scatter plot. For one thing, an outlier can mess up your R. So in other words, let's say you had some data that did this. Perfect linear correlation, except, whoop, we also had this data point. Well, that's going to mess up your R big time. Messes up the value of R big time. And so you might even conclude, oh man, there's no linear correlation here. What a bummer. But if you looked at your data, you'd say, wait a second. That seems to be an outlier. Now, I'm not saying just go throw it out, because for all you know, there's something real happening there. But you should take a closer look. And if you can justify, oh, look, he just copied the number wrong or whatever. If you can justifiably throw it out, you may save it and have a nice perfect R value, right? Nice perfect R equals +1 or something, R value. So it's always a good idea to look up, to do a scatter plot. You might find an outlier. Or remember the parabola thing, right? So you might find that this will give you an R equals 0 if you have some kind of parabola thing. But there's certainly a pattern. So you don't want to miss the pattern just because R is 0, right? So that's why you should always do a scatter plot. Second word of caution. We mentioned this on page 1. But again, make sure you never fall for this. Correlation does not imply causation. I love thinking up examples of this, so I've got a good example for you. Let's say you have, you ask somebody how many Pokemon cards they own, number of Pokemon cards that they own, and then on this one, it's how many beers do you have every week? Well, I'm guessing you'd probably find some kind of a positive correlation. I don't know how strong it would be, but I'll bet you there's some kind of a positive correlation there. So let's say you get a statistically significant positive correlation, right? Well, would you conclude that owning Pokemon cards makes you thirsty for beer. Makes one thirsty for beer. Or even vice versa. Drinking a lot of beer makes you want to go buy a lot of Pokemon cards? No, you wouldn't say that. You would not say that, right? Again, correlation does not imply causation. They just happen to go together. It just happens to be some kind of a relationship. Now, the relationship might be in the background. Maybe it's like age or something, because I'm guessing older people will drink more beers per week, and older people might have, well, they've been collecting Pokemon for a long time. They've got more money to buy the big booster boxes, whatever. So it might be that when somebody owns a lot of Pokemon cards, they're also drinking more beer per week. These are probably the kids over here, right? So the young kids don't have as many cards. They don't drink as many beers, I don't think, anyway, on average, you know. So correlation does not imply causation. Never fall for that. I use an absurd example, but usually they're going to try to tempt you with something that sounds good. Hey, look, the number of cigarettes goes this way, and the number of, I don't know, lung cancers or whatever go this way. There's probably a strong correlation. Now, in that case, there might be a cause and effect, but you can't just from the graph. You cannot conclude that, not just from the graph, not just from the linear correlation. And this one is huge, okay? You got to be very careful about this. Someday somebody might try to do this and you want to not fall for it. Your value of R is not even valid if each data point is representing an average for a group. It has to have, each data point should be a single individual, a single person with beer, a single whatever. It has to be an individual data point, not an average of like a group of N or something like that. Let's talk about, I don't know, bears. So I'll say individual bears. Maybe you measure their age and their weight, and maybe you find some kind of a linear correlation like that. Well, if you were to take the same data and kind of like package the bears into groups of 10, and then take that group of 10 bears and plot its age, its average age versus its average weight, well, you're going to get a correlation all right, but it's going to look a lot better. It's going to clear out the scatter. Scatter gets smoothed out. R gets massively overstated. Is that what I want to say? Overstated. The value of R will be too high. Don't use groups. Don't use groups. This is related to the idea of the central limit theorem. Remember when we sampled n at a time, we ended up getting a narrower standard deviation. It's kind of related to that idea. So groups are going to smooth out a bunch of variation. It's going to make your R look a lot better than it really is. So do not, try to remember this. Only individual. Do not group data together. Do not do averages of 10 bears at a time. Plot the age, plot the weight, call it a data point. Take another 10 bears, average age, average weight, plot the data point. Don't do it that way. Nope, nope. Okay, so I hope I made my point. Those 3 things to watch out for. Don't use groups. Correlation does not imply correlation. And make a chart. You might discover something. You might learn something cool. So this table, of course, you're going to need a little bit of Excel, just a little bit of Excel this week. And cool. So I hope you're digging on this correlation stuff.